My name is Nathan Sturtevant, and this is the master's thesis work of Junwen Shen. He's now a PhD student working with me at the University of Alberta. And unfortunately, he didn't get his visa to come, so I'm presenting for him today. But anyway, we're looking at the problem of, as the title says, of puzzle entropy. And so I'm going to give a little bit of an overview here. Because we have limited time, I'm going to actually skip a lot of the details, but I'm going to try and give you a taste of things. Be more than glad to talk to people later to give more details. So the question we're looking at is how can we measure the difficulty of a puzzle? And there's many, many algorithms, like genetic algorithms and some stuff that we do that, if you can tell me if something is difficult or not, then there's a lot of things I can do with that to get better generation or to evaluate players or other things like that. And so there's a lot of work that's been done that looks at, like in this particular puzzle, this is a great metric that you can use to try and come up with good solutions for that particular case. And we've been looking at trying to build more general tools that will allow us to measure that. And so last year we had a paper here at AIIDE by a different student, which was Eugene Shen, that was trying to look at the idea of entropy and trying to measure that in a puzzle. And what we're doing this year is it's basically an extension of that work. But we're trying to build a stronger theoretical foundation on what was done there. So we make some changes and do some theoretical derivations to understand what's going on. We have some new experimental results and some other pieces around that. So the problem definition that we're looking at has to do with puzzles. And so we're going to think about those, although it applies to other state spaces as well. And if we want to define what a puzzle is, we're going to define it as a state space that has a start state. All the examples in this talk are going to be taken from the game The Witness. And so this is an example puzzle from The Witness where you start from the circle in the lower left-hand corner and you're trying to get to the notch. It's usually in the upper right-hand corner, but in this sample puzzle, we put it in a slightly different location. So we have a start state, and the exact rules here aren't so crucial for what we're going to talk about in the talk. But anyway, so there's a start state. We have a goal state that we're trying to get to. And in this case, there's actually many goal states that you could get to. And this is just one sample one, which has a complete path that follows the constraints that exist in the puzzle. And then we have a successor function that tells us what are the actions that we can take in the world. What am I allowed to do? So in this case, I could start my path by moving it to the right. I could also start my path by moving it up. And those are the two possible actions that I could take here. And we could continue that until we got all the way to the goal. And so hopefully what you can see, at least from this first step, if you kept doing this recursively, what you'd end up with is you'd end up with an entire tree. I'm sorry, but before we get to the tree, the goal actually then is to get a path that gets you from the start to the goal at the end. So eventually you'd end up with something like an entire tree here. And just to show you at a high level, then we can think about, and I want to show the paradigm for what we were thinking about when we had the work we published last year. So the idea is that I am some sort of oracle, or I'm a teacher, and I'm trying to help you solve the puzzle. So we wanted to think about is, hey, you're at the start state up here at the top, and you're trying to get to the goal state down here. I'm going to think about how much do I have to tell you to guide you to get from the top of the tree to the goal, which is at the bottom of the tree. And so if we look at this, we can say, well, I'm sitting here at the top and I have a decision to make. So I can move left or right in the case of this tree. And then the answer is, well, actually you need to move to, I don't know, my right or left, something like this. So anyway, I make a decision of what direction I'm going to go. When I get there, hey, there's another decision to be made here. So in this case, I want to go left. So I'm going to make another decision to go there. In this case, I need to go again to the left. So I'm going to start walking down this tree. And so a teacher is actually telling me, like at each step, where I'm going to be going down this tree anytime I come to a meaningful decision. Now, at some points in this tree, there are places like here where I actually get to make many decisions at once. There's actually no choices to be made, but my path just follows down the tree. I have another decision here, and then I'm going to get to the end of the tree. Let's see, one more step there. Okay, so here I am at the end of the tree, and what this previous work did is it said, let's just look at the decisions that are being made here and the number of choices that we have. So at the root of the tree, we have one choice. The next node here, we have one choice, but there's two things we're choosing between. The next one, two things to choose between, and we can just walk down the tree. And overall, there's 5 different places along this solution path where we get to make decisions. And if we do this entropy calculation, which is it's just a standard formula here. It says, well, hey, there's 2 items. It takes 1 bit to tell you which of the 2 items to take. And so it would say that the entropy of this particular solution is 5 because there's these 5 decisions you have to make, and each one takes 1 bit to communicate. On top of that, there's a notion, though, that sometimes there can be decisions which are fairly straightforward decisions because, like, you know some information about the game or about the puzzle. So, for instance, here on the left-hand side, one of the rules of this is that when you have these black squares and the blue squares, they need to be split by lines. So they have to be in different regions in the puzzle. So right here, although nominally I have two choices to go right or to go down, what I actually can do is I just know I have to go down here. And it's not a real decision once I understand the puzzle. So we say, yeah, that's the right thing. You must, in fact, take that action. And the other action isn't one that you'd want to take. Similarly, this is a different rule that we actually developed in this paper. But here it looks like we have three choices: to go left, to go right, or to go up. But if we go to the left, what actually happens here is we've split this black star that is in the bottom right with the black square, and they actually need to be in the same region. So we'd immediately know that this can't be a solution. So we can take some actions and we can say, you should never take that action. And so if we go back to this tree here and we zoom in on this tree and we think about the nodes that are inside here, there were some that were cut off. Maybe, oh, there we go. And some of the nodes that are cut off there, then what happens is we see these nodes that are cut off, and these get cut off by these sorts of reasoning things that we get to do. So we basically put this tool together, then allowed us to do some very simple things to reason about a particular puzzle and to build these trees and think about what's happening there. And that was actually very successful in being able to predict which puzzles humans liked and which ones they didn't like, or they were upvoting on a website. But we had some questions coming from that. And so some of the questions were, what if I have something that's not just a rule that says you should do this and not do that, but I have a policy that says, like, in this situation, you should probably do this, but maybe you should do something else instead, and I don't want to have these 1 in 0 probabilities. And so these are basically policies that I can get. We also know that you can get policies from machine learning. So what happens when they get something from machine learning? And then some other things we did on top of that as we were exploring. So what I want to show you is I'm going to go through some of the things that were done theoretically fairly quickly, because it ends up that the end answer is really simple. It was really surprising, but the end answer is really simple. But I want to give you just a little bit of intuition, and I'll show you the great work that Junwen did, which you can find in the paper. And so this is the issue that we had when we started thinking about policies, as opposed to these just sort of binary decisions here. If we think about the entropy on the left-hand side, I have two choices. What we're really saying is that there's a 50% chance that you're going to take either of them. You measure the entropy is 1. But if I get on the right-hand side, which I had 1/5 and 4/5, then what happens there is that when you measure the entropy is lower because you have this distribution of what's going to happen. But if it ends up like, I can ask this question, well, what if the goal is on the left-hand side? If the goal is on the left-hand side, then I'm actually not very likely to get there, and that should be a hard problem. And if the goal is on the right-hand side, then I'm more likely to get there in my policy, and it should be easier. So we needed some way actually to distinguish between these two. And it comes from actually going back and looking at the foundation of the theory. So if we look at Claude Shan's theory, it's actually built of two pieces. One is the information content that says how much information is there when something happens in the world or if I communicate something to you. And then entropy is just the expected information. And so what we're going to do is we're going to back up and sort of stay in information instead of going into the expected information for entropy. It's a really small change, but it actually is really powerful in what it allows you to do. And so basically, we're going to change. So before we thought of this model of like a player, I'm telling them what action to take at each point in the tree. And the new model we're going to use is we have this policy that a player wants to play, which you can imagine that in the tree. And I'm going to communicate some information to that player, and it's going to cause them to shift their policy to some other policy in the world. And we're going to measure how much information do I have to communicate in order for them to shift the policy. So there's two versions of this. One, MSI is to find a single solution. TSI is to, well, I'll explain it in just a second, but it's to find any solution. So we can imagine a policy here. The middle branch is the most likely branch for the player to take at the root. But there's no goal states there. There's a goal state in the left and the right. And if I go to the left, then the goal state there is the most probable goal state for me to reach or in my policy. And so the idea of MSI is I'm going to choose a single solution, and I'm going to ask, what is the minimum communication I need to do to get you to that single solution, which will require the minimum amount of communication to get you there. And in this case, the policy would then have to look like that. So I'm measuring sort of how much communication I have to do to get you to this policy. If we go back to the original problem, because there are two solutions here, I can think about how much do I have to communicate to get you to any one of these solutions. And the idea is that since there's different probabilities on them, then I have to do some like optimization, like what is the correct probability that I want to put on each of these solutions that's going to minimize the total amount of information. And oh, sorry, that's not showing, but this is what the policy should look like. And these probabilities are balanced out here. So I just want to show you then some of Junwen's work, right? He did some definitions here in terms of using KL divergence, which is a measure that just measures how much communication is needed between two different policies. He developed that into this idea of total solution information, which is the total information that's needed. And anyway, I'll just show you some of the work that he did here. He did this, like, some calculus to find the minimization. And it ends up, after doing all this work, there's a very simple answer, which says, if I give you some policy that's telling me, pi, that's telling me what I'm going to do in the tree, and I want to know how much information it's going to take you to tell you to go to sort of this best policy that's always going to solve the problem, it ends up that all I have to do is basically say, well, I'm going to go here and say, what is the probability that your policy will reach the solution? And then I take the negative log of that, and that tells me the entropy or the information that I need. So it ends up that actually when we think about the probability of a particular policy reaching the goal is exactly telling me something about the information. Probabilities are very small numbers. They're hard to reason about when we convert them into information, or in the paper we call they're Shannon's. So this is a measure of information from Shannon's theory. Then we just get this really nice measure. And what that means is, like, on a really hard problem, you could just sample it and you can start to get you get an estimate of what the probability is. So there's lots of things you could do here now incrementally that would allow you to measure the difficulty of a particular problem. So anyway, so now we have this theoretical understanding. I'm just going to show you a small subset of our experimental results. There's quite a few that are in the paper. One of the things we were doing, though, is we're building a tool, and this tool is actually progressed from here, but it's a tool that allows us to take a puzzle. In this case, we have a partial puzzle, and we can put these question marks into the puzzle. This is what's called an EPCG query. It exhaustively will actually analyze each of these, and it'll give me back all the different puzzles we could create. Given this is essentially a query, what else should I put there? And it'll tell me which ones have the most information. Well, when you do this, sometimes it comes back with a puzzle, and it says, this is a really hard puzzle. And you say, no, this is a really easy puzzle. And generally what that means is there's some rule that I know that the generator doesn't know, and then we turn these things into rules that it could use. So we have some rules. Along the path rule says something about how paths are related to solutions, and we can do some inference here. I'm not going to describe them in detail. Another one is the region completion rule that says if you complete a region, we can evaluate it immediately. We don't have to wait till you solve the puzzle. So then we took a data set of solutions of puzzles that have been put on the windmill. So it's a little bit of an older set when the website was a little bit more active than it is now. And we evaluated those puzzles to say, like, how well do these measures correlate? And so it ends up that our new measures are fairly close to the old measures that were there, but because we made these changes, they're much more robust because they can handle policies. And then they also have this really strong theoretical backing on them. So we're going to look at some different subsets. I'm not going to show you the best results for a minute here, but I just want to highlight some things that we see. So one of the things that we see, this is a set of puzzles that have a constraint that are triangles. And on those puzzles, what we see is that it looks like humans are using one of these inference rules because we get a very high or higher correlation when we use that one. When we use the other inference rules, we get a much lower correlation. And so there's something here that says it's actually really important to think about what humans are using in terms of their inference rules. That's going to influence, whether we're generating good puzzles or not. What we see here, though, on a different set of puzzles, so these are ones that don't have triangles, then we don't see that same jump in the data. And so it's like that inference rule is really good on those puzzles, but it doesn't seem to be as predictive in other puzzles. One of the things we looked at then is we evaluated a machine learning model that had been created by one of my colleagues. And he just used this policy to learn how to play the witness puzzles. And now, because we have policies, we can actually ask, how well do these policies work? And what we saw is, although our inference rules can get a slightly higher correlation, the machine learning is actually doing a really good job of learning a high correlation of what humans actually find are likely to give upvotes on puzzles. So this is a really interesting result, and it's something that we could do now that we have this ability to evaluate policies. We actually then looked at the machine learning model, and what we could do internally is we could start to ask, like, which inference rules did it learn? And so what we see here is the top would be if we had a uniform policy, what would the probability of an action be? So, and we're going to go through a couple inference rules. So here, uniform, when this rule applied on average, there were basically two actions to choose between. Our inference rule says that you shouldn't take this particular action, and the machine learning policy also says basically you shouldn't take this action. So the machine learning had actually learned exactly this policy. There's another one here, which is a separation rule, but this is one where you had to take it, and we can see, yeah, it had actually learned that exactly. And the other situation here, I can't read my notes down here, but yeah, it said you shouldn't learn this, and the machine learning didn't learn it. But there was one of our other inference rules that it learned it a little bit, but didn't learn it a lot. So we can now actually look at this policy, and we can measure, what is it learning? Why isn't it learning certain things, or why is it learning certain things? Allows us to understand what's going on better there. Okay, I'm going to steal a minute of my question times. I want to describe one more thing here that we discovered. So on the left-hand side is a puzzle that a user posted on this site, I don't know, 6 months ago or something like this. And so I had this tool, and I solved this puzzle, and I said, this puzzle is a little bit easy. There's many, many solutions, and it's pretty easy to find a solution. But I put it into our tool, and then I ran the query, and it gave us back the puzzle that's on the right-hand side. And I can tell you, even now, if I go and try and solve this puzzle, I have a hard time doing it. And what seems to be going on here, actually, if we look at the upvotes, so they have approximately the same number of upvotes, but there's twice as many people who have solved the easy puzzle than have solved the hard puzzle. And what seems to be going on here is the inference rules actually, there are no inference rules which help you solve this puzzle. It's a little bit of there's some things you can still infer, but basically the standard inference rules don't help you solve this. And so you end up sort of wandering around trying to solve it. And it seems that actually players would prefer puzzles where the inference rules that they've learned will help them solve the puzzles, as opposed to finding puzzles where the inference rules don't help you at all. So there's something here that needs to be studied more about, how do we actually create good puzzles and use a good set of inference rules for the players that we have. But in this paper, to summarize here, what we have is we've introduced these new metrics of solution entropy. Total solution entropy is the most interesting one, where we're measuring this information that's required to help you find a solution. So these are very strongly theoretically grounded. They have good correlations with the puzzles that humans are enjoying. And anyway, so there seemed to be a good approach for use in practice. And we have this nice understanding that they really correlate to the probability of finding a solution. So this is really easy to apply in practice. And then really we're asking these questions, what can we apply this to a broader set of domains? Sudokus are very, very popular. So it seems like these ideas could be generalized there. It's work that we haven't done yet. And then this question about our player model seems to be really important to try and apply this. That's what I have for you today. Thank you for your attention, and I'd be glad to take questions.